Pawan? You start the recording also, then we will start.
Okay.
Yeah, now you can start. Yeah, please start.
Okay. So we are very glad to have Sandip Singh as our today's speaker. So he is a faculty at mathematics department in IIT Bombay. So let me quickly introduce you. His area of research is discrete subgroups of Lie groups, and his specific interests are monodromy groups of hypergeometric differential equations, monodromy associated to Calabi-Yau threefolds, and Coxeter groups. He is a student of Venkataramana, and today he is going to speak about hypergeometric groups and their arithmeticity. So over to you, Sandip.
Okay. Yeah, thank you very much, Supriya. Thanks for a nice introduction. And thank you, Devendra, and the organizing committee for this trimester program for inviting me to give a talk. Okay, so today I will speak about hypergeometric groups, and we'll discuss the question of determining their arithmeticity and thinness. So actually these hypergeometric groups are subgroups of GLNC, let's say n is a natural number, that arise as monodromy group of some monodromy group of hypergeometric differential equation of degree n. So n is associated to that. And if we put some certain conditions,
are you moving your slides?
No, not. Don't worry. No, and if we put some certain conditions on the hypergeometric differential equations, then we have some information about their Zariski closure. As I said in the beginning, that these hypergeometric groups are subgroups of GLNC, and they arise as monodromy group of some hypergeometric differential equations. So with those conditions, we know that we have information about the Zariski closure of those hypergeometric groups inside GLNC. So suppose G, so basically, suppose gamma is a hypergeometric group, and that I already said that is a subgroup of GLNC, and this gamma is associated to some hypergeometric differential equation. And that I will tell in more detail that how these hypergeometric groups are monodromy groups of some hypergeometric differential equations. So now let us denote by Z as Zariski closure of gamma, and so forth. This is inside GLNC. Right? So and then we'll see that if we put some more conditions on the differential equation, then we get that actually this gamma is contained inside the integer points of this algebraic group G. And we call this gamma arithmetic if the if index of gamma we write like this. I have not taught basic algebra since a long time. If this index is finite. So in other cases we call this gamma thin. So basically, we'll try to determine the hypergeometric differential equations whose monodromy groups are arithmetic.
Sandip, your voice is gone. Hello, Sandip.
Yeah, and
now you are audible. For a minute, your voice was gone.
Thanks, Supriya. Please keep letting me know. And no, something happened with my Bluetooth headphone. It got disconnected. Okay, I'll up. So with this arithmetic and thin hypergeometric groups, so basically we'll try to determine the hypergeometric differential equations whose monodromy groups are arithmetic are thin, and also as we have seen several times in some of the lectures in the series, that there are 14 families of Calabi-Yau threefolds that are hypergeometric. Actually, we saw in last lecture in very detail in Ifan Young's talk. So in this talk, actually, we'll discuss the question to determine the arithmeticity and thinness of the 14 hypergeometric groups that are associated to Calabi-Yau threefolds. Yeah, so with all these motivations, let us start formally by defining the hypergeometric differential equations and their monodromy. So, yeah, at the beginning, we fix this notation theta for the differential operator, the z d by dz, and alpha 1, alpha 2, alpha n, beta 1, beta 2, beta n are complex numbers. For them, we write this differential operator d alpha beta as theta plus beta 1 minus 1 dot dot. This is product theta plus beta n minus 1 minus j times theta plus alpha 1 dot dot theta plus alpha n. And if we expand this bracket, then we know that the highest coefficient will be the polynomial z to the power n times 1 minus z. And then, then means these PIs are actually polynomials with complex coefficients. So this d alpha beta is a differential operator of this kind. And then we consider the hypergeometric differential equation d alpha beta u is equal to 0 on P1 minus these 3 points. So P1 is basically the Riemann sphere, that is 1 point compactification of complex plane. So P1 you can think of C union infinity with that topology. Right. So we are considering this differential equation d alpha beta u is equal to 0, where d alpha beta is this differential operator, and then means we get that this differential equation for d alpha beta defined like this has regular singularities at points 0, 1, and infinity, and it is regular elsewhere. So yeah, we say that suppose some point z naught in this P1 minus 0 and infinity is a regular singularity of this differential equation. It means what we do means if you just divide, yeah, basically, let me. No, means like that if we expand that differential equation was of the type a naught j dn dzn u plus a1z dn minus 1 dzn minus 1 u plus a and z u is equal to 0, right? So we call that a point z is equal to z naught is basically in C, right? In P1 minus 0 infinity. So in C, it's said to be a regular singularity of this equation. Let's say this is a star. If so, this is the like. First of all, like a naught, z naught should be sort of means yeah, no need to say that. So we can directly say that the ai means where these coefficients are. We have seen already these coefficients are polynomials with complex coefficients. So aiz by aiz by a naught z has a pole at z naught of order at most I. And then we call that z naught is a regular singularity of this equation. And also we know that this is 0 if and only if you satisfy this differential equation, right? dn u by dz n plus just divide by the highest coefficient. So a1 z by a naught z dn minus 1 dz n minus 1 plus a n z by a naught z is equal to 0. Yeah, so this is how means singularity. Anyway, we know means what is singular point for a differential equation. That is called regular if this quotient of two polynomials aiz and a naught has a pole at z naught of order at most I. And this is very much clear, no? Because here the highest coefficient is the polynomial z to the power n times 1 minus z. It is clear that this equation d alpha beta u is equal to 0 has a regular singularities at 0 and 1. And just to test for infinity means you just need to transform z to 1 by z. By that transformation, you can see that infinity is also a regular singularity of this differential equation. And Yeah. And now let us fix a point Z0 in P1 minus Z1 infinity. And suppose this pi1 denotes the fundamental group of P1 minus 3 point based at Z0. So we all know that this fundamental group, this pi1 is basically is the fundamental group of C minus 0 and 1, right? And that is same as fundamental group of figure 8. And that is actually a free group on 2 generators, right? And also, like if in this case, if you include the loop around infinity also as inside the generating set, then we get that this pi1 is actually generated by Z0, Z1, G infinity modulo this single relation, G infinity, G1, G0 is equal to 1. Where G0 is, as we know that we understand by the notation that this is path homotopy class of loop around 0. G1 is the path homotopy class of loop around 1, and so is infinity, G infinity. Right? All are based at Z0. So with this, now we define the monodromy action of this pi1, the fundamental group of P1 minus these 3 points on the solution space of this hypergeometric differential equation.
I just want to recall a thing. There is this classical Gauss hypergeometric equation, and you are here considering nth order. So the regular singularity and
same, both
are same, right? And so,
yeah. Means regular singularity, what I just defined, means regular singularity means like, yeah, that only.
I think
in that case also, n is equal to 2 also.
Hypergeometric equation is defined like that. It has a regular singularity. All its singularities are the regular.
Yeah, means yeah, means all correct. All singularities are regular singularities, and means that hypergeometric means like it has regular singularities only at 0 and infinity, and it is regular everywhere else. It is clear enough from this highest coefficient.
Yeah, but yeah, so for Gauss classical case, I know that they are defined like that, but in general case,
in general also.
Okay. Okay, then.
Okay, so with that, let us define the monodromy. That also we have seen in very detailed in Boyker's and Ifan's talks. And I'll just quickly go through this. So the monodromy action of pi1 on the n-dimensional solution space, let's say V of this differential equation on a small open disk U. Suppose U is a disk centered at Z0, and that is inside P1 minus 0 and infinity, is defined by analytic continuation of fundamental solutions along the loops generating pi1. So I guess means basically you know, means like if I means you get a disk centered at Z0 of a small radius, where the differential equation means that is of degree n is a regular equation, means on that U. So therefore you get that the solution space of that equation is n-dimensional. So you can fix a basis containing n linearly independent analytic functions, right? And then what we do means just by analytic continuation along suppose loop G0, and if you come back to the same neighborhood U centered at Z0, then this means we get another set of n linearly independent analytic functions that are solution of the same differential equations. Right, so we can write the it's like sort of like we get the change of basis matrix corresponding to each loop. Okay? So that's how means the action of G0 is defined by the matrix which changes that basis. Like if you fix the basis upon FTFN, so and then we get the new basis CH1 to HN of the same solution space. So that's how actually monodromy action is defined, and means other things can be fixed just by using the Cauchy's theorem that if two loops are homotopic, then the corresponding analytic continuations are identical. And if you take the product, respect the product in matrices. So that's how we get a very nice group homomorphism from pi1 to GLNC, means that way. And that is called the monodromy representation of pi1, and rho pi1 means image of pi1 under rho, which is clearly a subgroup of GLNC, that is called the monodromy group of the hypergeometric differential equation. Now, very nice characterization of monodromy groups are given by Livell. All such results we have heard many times in this program. So by a theorem of Liouville, if alpha 1, alpha 2, alpha n, beta 1, beta 2, beta n in C are such that alpha j minus beta k is not an integer for all pair of j and k between 1 to n, then the monodromy group gamma alpha beta of the hypergeometric equation d alpha beta u is equal to 0. Remember that d alpha beta is defined by d alpha beta denotes this differential operator, theta is z times d by dz. Yeah, then the monodromy group of this differential equation is up to conjugation in GLNC, a subgroup of GLNC generated by the companion matrices A and B of the polynomials fx and gx. So roots of the polynomial f are e to the power 2 pi a alpha j, and roots of g are e to the power 2 pi a beta j, where alpha j and beta j, they define the differential operator d alpha beta. So basically conjugation means like we get means there exists a basis of the solution space with respect to which the monodromy matrices are actually companion matrices of these polynomials f and g. And the monodromy representation of pi 1 is defined by sending this g infinity to A, g naught to B inverse, and g1 to A inverse B. Moreover, if sigma is any representation of pi 1 into GLNC such that the characteristic polynomials of sigma g infinity and sigma g naught inverse are f and g, since f is this and g is this, respectively, and sigma g1 minus identity has rank 1, then sigma is the above representation. Like both representations are isomorphic. Okay? And we have one thing we should just note down to follow this lecture closely, that means like if you just expand, so fx is the polynomial, means fx is of course a monic polynomial, right? So that is of the type x to the power n plus let's say n minus 1, x to the power n minus 1 plus a1x plus a naught, and gx will be x to the power n plus bn minus 1, x to the power n minus 1 plus b1x plus b naught, right? Means if you expand this f and g, then they are monic polynomials with constant terms a naught and b naught. And the matrix A is companion matrix of F. So by definition, you can recall that this companion matrix is like lower diagonal entries will be 1, and the last column vector is negative of the coefficients of F. So minus A naught minus A1 minus an minus 1, and this will be 1, and rest of the entries are 0. Right? And similarly, you can write B also. Right? So you see that what the A does, A is actually sending E1 to E2, E2 to E3, En minus 1 to En, and En to minus A naught, E1 to minus A1, E2, and so on. And so does B, right? So what about A inverse B? A inverse B sends Ez to Ez. Right? B will send Ez, means yeah, for all j, let me say less or equal to n minus 1. So B will send Ez to Ez plus 1, and A inverse will pull back Ez plus 1 to Ez, right? So A inverse B sends Ez to Ez, and what about so, and then A inverse B En, means for j is equal to n, will be what? This will be you can actually check that C times En plus some linear combinations of that. E1, E2, En. So if you just write down this matrix A inverse B with respect to the same this basis, standard basis E1, E2, En, then we get that this A inverse B generally will be denoting as C. So C is nothing but a unipotent matrix. And the last column, this one, the other entries are 0. So basically, the C is a unipotent matrix for which C minus I has means C. There it was written as A inverse B minus I has rank 1. Right? So so this is how, means if you write A and B, so you can check that C, the matrix C, which is A inverse B. Yeah, this entry is C, no? Sorry, small c. I mean C, not 1, not sorry. No, means it is not. Remember, this C will appear here, means yeah. But still, we see that A inverse B minus I has rank 1, right? In general case, C need not be a unipotent element. Yeah. Yeah. So, and this A and B generate the monodromy group gamma that we are denoting as alpha beta as a subgroup of GLNC generated by okay. So
so this matrices you constructed from the polynomial and generated the monodromy group of the differential equation, right?
Correct. Yeah. Yeah. Means yeah, Lewis theorem says that up to conjugation, like you will get the basis of that solution space with respect to which monodromy group is actually the subgroup of GLNC generated by those two matrices A and B, where A and B are companion matrices of these two polynomials F and G. Okay, so yeah, now means yeah, and yeah, now onward we'll call the monodromy group of hypergeometric differential equation hypergeometric groups. I mean, yeah, actually, hypergeometric group has in Boyker's and Ekman hypergeometric group it just defined means like the group which is satisfying this condition. Like it will have 3 generators and means like yeah, one of generator like sigma means this G1 minus I will have rank 1 and so on, and we get that monodromy group of hypergeometric equation. If this alpha j minus beta k does not belong to Z, then that monodromy group is actually a hypergeometric group, and we call that
no reference to the hypergeometric equation. No reference to the hypergeometric equation.
No. Hypergeometric group is defined independently. That can be defined. Just we need 3 generators where there is only one relation like G infinity, G1, G0 is 0, and means there are like subgroup of GLNC, subgroup of GLNC I'm saying, and where the condition is like A inverse B minus identity has rank 1.
I see. So if we define hypergeometric group like this, can we realize always with some hypergeometric equation?
Yeah, there is a hypergeometric equation whose monodromy group is that.
Yes. Okay.
Yeah. In fact, that is very nicely done in that Boyker-Ekman Sinha paper.
Okay.
So yeah, and then Lewis theorem actually gives characterization of hypergeometric. Okay, so we'll call this monodromy group of hypergeometric differential equation, means we'll address them as hypergeometric group. Now we'll discuss that means how thick are these hypergeometric groups inside GLNC. So presumably we'll be calculating the Zariski closure of these groups. So we consider yeah, just for convenience, we consider FG as integer coefficient polynomials with constant terms plus minus 1, so that the associated hypergeometric group is actually a subgroup of GLNZ. Right? You understand now? Like the constant term actually determines the determinant of the companion matrix A and so B. So we are considering that means just to make sure that gamma fg is contained inside GLNZ, we are considering integer coefficient polynomial with constant term plus minus 1, so that the determinant of the corresponding companion matrices are plus minus 1. Then Boyker and Ekman showed that if FG are self-reciprocal and form a primitive pair, self-reciprocal basically means that if A is a root, then 1 by A is also a root of M, and so is G. And they form a primitive pair. Primitive pair means that F and G cannot be written as polynomials in x to the power k for some k greater or equal to 2. See, this pair are self-reciprocal and form primitive pair. Then, depending on the constant terms of the polynomials Fg, the corresponding hypergeometric group gamma Fg preserves either a non-degenerate symplectic form omega or a non-degenerate quadratic form Q. So, in fact, it is determined like this: if the constant terms of F and G are 1, then gamma Fg actually preserves a symplectic form omega, and gamma and the Zariski closure of gamma Fg means the hypergeometric group gamma Fg is full of the symplectic group. And if F0 by G0 is -1, then gamma Fg preserves the non-degenerate quadratic form Q, and gamma Fg sits inside the integral orthogonal group as a Zariski dense subgroup if it is not finite. So the Burgers and Heckman also determine the conditions when these hypergeometric groups are finite. So actually the cases where these indices alpha and beta, if they they satisfy some interlacing condition. So so in that case we get that gamma Fg is finite, and in other cases we see that just gamma Fg is Zariski dense inside the orthogonal group. And also one can ask that here we are saying that means gamma Fg preserves a non-degenerate symplectic from omega. So no restriction on n is given, right? Means, and we know that this gamma means this omega a symplectic form in n variable is non-degenerate if and only, not if and only, means at least like the necessary condition is n must be even number. So you can check that with this condition because we are considering f and g self-reciprocal, and also like to use the Level's theorem, we have assumed in the beginning that f and g should be coprime polynomials. F and g should not have any common root, and f and g are self-reciprocal. These two conditions ensures that f0 is equal to g0 is equal to 1 is satisfied only when n is an even number. Otherwise, you will see means if n is odd, then this condition holds only if -1 is root of f and g both, but that is not allowed. So this is how we get the Zariski closure of the hypergeometric group that we are now denoting as gamma Fg inside GL and C. Yeah. So here is a definition. So let this G be the Zariski closure of the hypergeometric group gamma Fg inside GL and C, and gamma Fg sits inside the points of that group G. Then gamma Fg is called arithmetic if it has finite index in Gz, and thin if it has infinite index in Gz. Means I think it's a good point. Means because Professor Kulkarni is not here, while watching the Ifan Yang's lecture video on YouTube, and she had asked some question like, to be thin, is it necessary to be discrete? So basically, thin groups are means like discreteness is part of definition of thin group. Like some people say that or discrete, and there are several results like a discrete group. Discrete subgroup of a real Lie group, a real algebraic group means we say is a lattice if GR mod gamma has a finite measure, right? And then by Borel density theorem, we know that if gamma is a lattice inside G, we can assume that G is simple group, right? So that gamma is by Borel density theorem. We know that gamma is if gamma is a lattice, then gamma is Zariski dense inside G. Right. So, in some sense, we are saying that lattices are discrete and Zariski dense. Right. So, right, and then we get by Borel Harishchandra that means that arithmetic group is defined like if G is algebraic group defined over Q. Then any subgroup of GR which commensurate with the integer point of G is called arithmetic group, and Borel Harishchandra theorem tells that all arithmetic groups are lattices, right? So then we get that arithmetic groups are Zariski dense, and being GZ are discrete also, right? So just to means like arithmetic groups have very nice property, means that is a lattice means Zariski dense as well as it is a lattice, like quotient has finite measure. But there are other kind of discrete groups that are Zariski dense, but they are not a lattice. But they are not a lattice. So such groups are called thin groups, and some people include that finitely generated condition also part of thin groups.
So discreteness is part of their definition.
Discreteness is part of their definition. Right, it's basically, I think, means I have tried to motivate means how it comes, like they are sort of countering arithmetic groups. Arithmetic groups are dense as well as their quotient has finite measure, means like they are lattice by Borel Harishchandra. And these groups are also discrete subgroups. They are Zariski dense, means right, but the quotient does not have a finite measure. So such groups are called thin.
Okay.
And in our case, we know that means just gamma is already Zariski dense inside G. And if gamma is contained inside GZ, and we know that GZ is a lattice, right? So gamma can be thin only if
what happened? You are not audible now.
Sandip, we lost your voice. Sandip, is there again problem with the Bluetooth?
Again, yeah, I'm sorry.
Yeah, no problem. Just you can. It was just for maybe 30 seconds or something.
Yeah. I don't understand why it is getting disconnected. Yeah, now it should be okay. You can now hear me, no? Hello?
Yes.
Oh, okay. Yeah, thanks. Okay, so
infinite index thing is equivalent to that other thing you are telling, infinite measure.
Yeah, correct. Of course, no, means if gamma fg is already a subgroup of gz, if gamma fg is a finite index in gz, no? So gamma fg cannot be a lattice. Then gamma fg will also be a lattice. The quotient it is discrete being inside gz, and we want it to be thin. Like means the quotient should not have a finite measure, so it has to be a finite index inside gz. If it is of like, if suppose gamma fg has finite index in gz, so in some sense this is again arithmetic. So we are not getting anything about non-arithmetical self. And yeah. Okay, so yeah, so we know means like if it is thin, means like the being thin, it can't be a lattice inside Z. Yeah. Okay. So we now address the following question. So determine the hypergeometric differential equations whose monodromy groups that are being called as hypergeometric group are arithmetic or thin groups. So observe that determining a hypergeometric differential equation is equivalent of determining the pair of polynomials that determines the corresponding hypergeometric group, thanks to the Liouville's theorem. Here is an answer to that question in symplectic case. So note that in this case, f0 is equal to g0 is equal to 1. The constant terms of both polynomials are 1. And Boyker's and Heckman conditions, coprime and self-reciprocal, that ensures that degree n of the polynomials f and g must be an even number. So then we give a sufficient condition on the pairs of polynomials fg of degrees at least 4. So that the associated hypergeometric group gamma fg is arithmetic. So here is the theorem that we obtained in my thesis. So if the leading coefficient, like just consider the difference polynomial f minus g with all these Boyker's and Heckman conditions on f and g. If the leading coefficient c of this difference polynomial f minus g satisfies the condition that absolute value of c is less or equal to 2, then the hypergeometric group gamma fg associated to the pair fg is an arithmetic subgroup of the corresponding symplectic group. Okay. So if you have integer coefficient polynomials satisfying Boyker's and Heckman conditions for symplectic case, then you, if someone asks that what is the what kind of like what is the if the associated hypergeometric group to that pair is arithmetic. So this is just, this gives a sufficient condition. Like if you know that f minus g has leading coefficient plus minus 1 or plus minus 2, then you can immediately tell that the corresponding hypergeometric group is arithmetic using this theorem.
From where is symplectic coming?
Symplectic means like this condition, f0 and g0 is 1. If f and g satisfies this condition, then we know that gamma fg is contained inside, like gamma fg actually that hypergeometric group preserves a non-degenerate symplectic form,
Okay,
and it sits inside the integral symplectic group of that form as a Zariski dense subgroup.
Yeah, okay.
Right. So here is one remark. So our theorem even holds for n is equal to 2. So in this case, you know, means f will be this polynomial, like x square plus a1x plus 1, gx is x square plus b1x plus 1. Right? For symplectic case, we require that f0 is 1, g0 is 1. And c, the difference leading coefficient of this difference f minus g is nothing but a1 minus b1. And in that case, we get that this a is component matrix of f and b is component matrix of g. And if we just write A inverse B, then A inverse B is nothing but this unipotent matrix where diagonal, unipotent matrix is 1 C0 1, and AB inverse will be 1 0 C1. Right? So we get that these two matrices, right, 1 C0 1 and 1 0 C1 are contained inside the hypergeometric group associated to the polynomial f and g. Right? And we know that if C is, for example, plus minus 1, then these two matrices it will generate full of SL2Z. And if C is plus minus 2, then they generate a finite index subgroup of SL2Z. So yeah, basically these two matrices generate the index 2 subgroup of gamma 2, congruous subgroup of level 2. So in fact, for C is equal to plus minus 2, means this the subgroup generated by these two matrices actually has, means one can calculate that the index inside SL2Z is 12. Okay? So they contain these two matrices, the hypergeometric group corresponding to F and G contains these two matrices that they generate a finite index subgroup of SL2Z, which is same as SP2Z. And also one more information on this is that if C is plus minus 2, then these two matrices actually generate a free subgroup of SL2Z. And one can prove very easily that that subgroup generated by these two matrices inside SL2Z is free by using the ping pong lemma. So that will talk soon in the next 5 minutes. So and the assumption on C, assumption C plus 1, this was the dish. So I already explained that. So why means that our theorem means where we assume that n should be greater or equal to 4. Actually, that holds for n equal to 2 also. And but this result, the result what I just stated, these are the classical results. Means we're very well known. And now let us talk about monodromy associated to Calabi-Yau threefold. That is basically theme of this trimester program. So we now consider the case when fx is x minus 1 to the power 4 and gx is product of cyclotomic polynomials. G0 is 1, G1 is non-zero, and fg form a primitive pair. Right? Because one is the polynomial of f and we want the g such that f and g are co-prime, right? So one cannot be a root of g. So this is why, and cyclotomic polynomials, you remember, no? Like cyclotomic polynomial of degree 1 is x plus 1, x minus 1, right? X square plus 1 for degree 2 means there are several means x square plus 1, x square plus x plus 1, and so on. So that kind of like basically this g is the integer coefficient polynomial. G0 is 1, and the roots of g are roots of unity. Actually, means I want to say that roots means only roots of unity are the roots of this g. So observe that in this case, gamma fg is contained inside sp4z. Means gamma fg is symplectic. And if you just, it is not difficult to write all possible pairs of f and g, because we know that all cyclotomic polynomials of degree, right, of any degree actually. So you can just try to write down the pairs that satisfies these conditions of Boykers and Heckman. So basically, we get that there are total 14 pairs of polynomials satisfying the above conditions. And then by the work of Pendelas et al., the hypergeometric groups corresponding to these 14 pairs of polynomials are the same as the images of the monodromy representations which arise from families of Calabi-Yau threefolds. It's those 14 families of Calabi-Yau threefolds, in fact. So in fact, there are 14 families of Calabi-Yau threefolds which fiber over the space P1 minus G1 infinity, for which the monodromy action actually correspond to the homomorphism that since G infinity is again mathematical class of the loop around infinity, means G infinity, G naught, and G1 means the generators of the fundamental group of P1 minus this 3 point. So just by sending G infinity to A, G naught to B inverse.
Just can you repeat why there are just 14 pairs of polynomials?
No, this you can write. No, means actually cyclotomy. For each n, means you understand how the cyclotomic polynomials are defined. That is basically x to the power n minus 1 divided by means something like phi d, corresponding to the divisor d of n, means we divide phi d of x.
Okay, some property of
so basically we know like phi 1x is x minus 1. Yeah, phi 2x is x plus 1 because it should be x square minus 1 by x minus 1. Phi 3x is x square plus x plus 1, right? Phi 3x is like x power 3 minus 1 divided by means product of phi d where d divides n, right? So phi 3x is nothing but x square plus x plus 1. Phi 4x is x square plus 1 and so on. Phi 5 is like x power 4 plus x cube plus x square plus x plus 1 and so on. Okay. So you have that limited choice of cyclotomic polynomials, and f is fixed. So g can be like, what are the possible? I will show that what are all possible g. So g can be x plus 1 to the power 4, right? G can be x square plus x plus 1 whole square, right? And g can be x square plus 1 whole square. G can be x power 4 plus 1. Okay? So all such g, if you write, there are only 14 pairs actually that correspond to those 14 families of Calabi-Yau threefold that are hypergeometric. And then means now we know that what are the monodromic groups of that 14 families of Calabi-Yau threefolds that fiber over this P1 minus 3 points. So then the next question is means like then one can ask means which of them are arithmetic and which of them are thin. Right? Then thanks to this criteria, this characterization of Pendelas et al., that we know that those 14 groups that arise as monodromic group of these 14 families of Calabi-Yau threefolds are actually a hypergeometric of 14 family of 14 hypergeometric groups. So that is basically written in this list. So in this list, actually the polynomial f is x minus 1 to the power 4, and if you expand, there's nothing but x power 4 minus 4x cubed plus 6x square minus 4x plus 1. And from beta, it is clear the g is, for example, like square of the sixth cyclotomic polynomial. So that is what x square minus x plus 1 whole square. So this g is nothing but x square minus x plus 1 whole square. G in number 2 is what? This is x plus 1 to the power 4. Again, this is x square plus x plus 1 whole square.
Can you explain beta again?
No, beta is like this corresponding to beta. What is the root of f? Root of f is like sixth root of unity. And also we have to make sure that this g is actually integer coefficient.
From where you are getting beta?
No, beta means I have written in terms of beta, but from a polynomial only. So if you consider the sixth cyclotomic polynomial, that is something like x power 6 minus 1 divided by phi 1 times phi 2 times phi 3, then you get that polynomial actually is phi 6, you can say phi 6x is x square minus x plus 1. It is not very difficult. It's that we students while studying the Galois theory. No, it's like this is actually, this determines that we are considering the sixth cyclotomic polynomial. It's the cyclotomic polynomial which has primitive sixth root of unity as root. So from here, just by looking at means if you know the polynomial cyclotomic polynomial, then you know the roots. So it is just basically it tells that e to the power 2 pi I by 6 is a root of g.
Okay. Right? And similarly, e to the power.
Similarly, means this is physics.
5 pi 10 pi by 6?
Correct. Yeah. 5 means, yeah, correct. 10 pi by 6 is also a rule.
Okay.
So basically, it means that polynomial having the root corresponding to
These
5
roots,
by
yeah.
6 is x square minus x plus 1.
Mhm.
And this is just basically repeating. Na? So x square minus x plus 1 whole square is g.
Mhm.
And this is the second dynamic polynomial. So this is like x plus 1 to the power 4.
Mhm.
And here we get x square plus x plus 1 whole square. Like in fourth case, we get x plus 1 whole square times x square plus x plus 1 and so on. So you get only these 14 pairs, means 14 possible G corresponding to this F, so that the corresponding hypergeometric group is symplectic. And the interesting thing is, like in the case number 1, you see that if you look at F minus G, then the leading coefficient of F minus G is minus 2. So just by looking at the leading coefficient, that it turns out to be minus 2 here, which has absolute value 2, it immediately follows that one can immediately say that the corresponding hypergeometric group is arithmetic, just by using our theorem. Okay? And then means up to some extent, just by using the proof of that theorem, we in the same paper we also proved the arithmeticity of the cases 11 and 13. And where clearly you can see that the leading coefficient of the difference polynomial turns out to be bigger than 2 in absolute value, but still the associated hypergeometric groups are arithmetic.
And require something else. This the last thing you said is still arithmetic.
No, this one I'm saying that the 11 and 13.
Okay.
11, 13 has leading coefficient minus 3, right?
Mm-hmm.
But the corresponding groups are arithmetic, and the groups mentioned by group I mean the pair of corresponding polynomials mentioned in red are actually thin groups. So we actually see that 7 of them are blue and other 7 are red. Blue are arithmetic and red are thin. So I'll just talk about a little bit of a proof. So yeah, here is the dichotomy in the case of 14 hypergeometric groups. So Brav and Thomas actually showed that 7 of the 14 hypergeometric groups are thin. So they actually use the ping pong lemma that is already known. I gave one classical example of a free group of subgroup, free subgroup of SL2Z, generated by those two matrices like 1, 2, 0, 1, 1, 0, 2, 1. And there also the freeness is proved just by using the ping pong lemma. So they use this Brav and Thomas also use the ping pong lemma to show that 7 of the 14 hypergeometric groups are either free groups or contain a free subgroup of finite index, and hence they can't have finite index in SP4Z. So basically, there is something called cohomological dimension of this SP4Z that is actually 2. And this is also a general result that if you consider any finite index subgroup of SP4Z, then the cohomological dimension of that subgroup is also 2. But free groups have cohomological dimension 1. Right? So as soon as you get that some hypergeometric subgroup of SP4Z is free, they can never have a finite index. Okay? So prove the thinness in these cases. It was enough to show that these 7 groups are either free or they contain free subgroup of finite index. And using the theorem and its proof, we with Venkatramana showed that 3 of the remaining 7 hypergeometric groups are arithmetic. And later in 2015, in my postdoc, I actually showed that the remaining 4 groups are also arithmetic. So we showed that these 7 hypergeometric groups contain enough unipotent elements to have finite index in SP4Z. So there's some certain criterion to show arithmeticity. Like for example, like if you can show that the
Yeah, again or not audible.
Yeah, but I'm sorry. I knew that what is happening, so I did not speak. Okay. So I don't know. Means this is, that we can never taste. No, means I don't know that whether like after 20 minutes it's going to get disconnected.
No, that's okay. It's a very minor interruption. No problem.
And now I know, so I will stop.
No problem. Continue, Sandip.
Okay, so actually means there are some certain criterion to prove arithmeticity. Like for example, if you can show that means if you take you consider the Borel and consider the corresponding parabolic subgroup, and if you can show that if gamma fg, that is a Zariski dense, and it intersects the integral parabolic subgroup in a finite index, then that has finite index in SP4J. Or even means it is sort of easier criteria was given by Venkatramana. Means for that you just need to check that because SP4 has a very nice root system. So if you can show that the gamma fg that is contained inside SP4J contains elements corresponding important elements corresponding to the highest and second highest roots, then you get immediately that gamma fg is of finite index, or gamma fg is arithmetic. Zariski denseness is required, but that is anyway there by Kersenbeck. So this is how half of the 14 hypergeometric groups associated to Calabi-Yau threefolds are arithmetic, and the other half are thin. Okay, so here means I will mention some recent results. So the general case of the maximally unipotent monodromy. So like the and we know that if you consider the polynomial f as x minus 1 to the power 4 and write down its companion matrix as A, then we know that A is maximally unipotent matrix. Like all the roots of A are 1, and the maximally unipotent means x minus 1 to the power n will be 0, but x minus 1 to the power n minus 1 will be non-zero. Okay, so by maximally unipotent monodromy we mean matrix of that kind. So similar to the family of 14 hypergeometric groups associated to the maximally unipotent monodromy, there is a family of hypergeometric groups with the maximally unipotent monodromy. Means so corresponding to fx is equal to x minus 1 to the power n inside SPN for any even number n. The same way, you can consider x minus 1 to the power n, and then consider g all possible g that are integer coefficients constant from 1, and the roots of g are roots of unity in the same way. Like g is the product of several dynamic polynomials such that the pair f and g satisfy the Boyker-Sackman conditions. So then one may ask if these families for n greater or equal to 6, for n is equal to 4. In fact, n is equal to 4 we know already. N is equal to 2. All the groups are actually arithmetic. So that's why I've written n greater or equal to 6. Also follow the dichotomy between arithmeticity and thinness similar to the degree 4 cases. So the first case to answer this question is n is equal to 6, where f is given by x minus 1 to the power 6, and the corresponding family contains actually 40 hypergeometric groups. So one may notice that 40 is an even number. So one may expect that 20 of them are arithmetic and other 20 are thin. Okay. So in our effort to provide an answer to the above question, we obtained the following theorem. So this is a theorem obtained jointly with Bombay, Dona, and my PhD student Singh. We actually showed that 18 of these 40 hypergeometric groups are arithmetic in SP6. And the above theorem is proved by using the following criterion, means that is already remarked in Singh and Venkatramana, that extends the arithmeticity criterion of Singh and Venkatramana. So here is a criterion that is remarked in that paper. So let the leading coefficient of the difference polynomial f minus g has the absolute value greater or equal to 3, and let e1, e2, en be the standard basis vectors in Qn over Q, and I be the identity n cross n identity matrix. Let this V denotes the last column vector of C minus identity. V is C minus I of En. Basically, this is the last column vector of C minus I, where C is A inverse B. All that we know means how is A, B, and how does this C look like. So if there exists an element gamma and gamma fg inside the hypergeometric group, like if there is a word gamma, if there is a gamma that is a word in A, B, A inverse, B inverse, such that these three vectors v, gamma minus v are linearly independent, and the coefficient of En in gamma v written as linear combination of the standard basis vectors has absolute value either 1 or 2, then the hypergeometric group gamma fg is arithmetic in the corresponding symplectic group. So this is not new, exactly the same proof of this Singh and Venkataramana actually that works in this case. We have to just replace summation to the power k by this word, this element gamma and gamma fg. Right. So here we get now that if v is that vector, last column vector of c minus identity, and if you have a word gamma in gamma fg, such that gamma v has leading coefficient, like gamma v is a vector inside Qn, right? So if the coefficient of En turns out to be plus minus 1 or plus minus 2 for this gamma or any such gamma, then we immediately get that the corresponding hypergeometric group is arithmetic. So here is a phase math program to find a gamma as a verb. So it follows from the last proposition that one can show the arithmeticity of a symplectic hypergeometric group by finding an element gamma in gamma fg if there is any that satisfies its hypothesis, right? Because anyway, means we know that v is the last column vector of c minus identity, right? So we have to just find the gamma such that that vector v, gamma of v, and gamma inverse of v, like that set of three vector is linearly independent, and gamma v has that last coefficient having absolute value plus minus 1 or plus minus 2. Right. So if we get such gamma, then we get the arithmeticity immediately. So recall that gamma is a word in AB, the companion matrices of FG respectively. So I should say that this is a word in AB, A inverse, B inverse, where A and B are companion matrices of F and G. So verifying the criterion of the last proposition with one gamma after another doesn't seem an easy task. So one can ask whether it is possible to write a computer program that can help in finding an appropriate gamma. So the answer to this question is yes, and we in the same paper also provide a SageMath program that finds a gamma if there is any of some particular length satisfying the hypothesis of the proposition. So we use this program to show the arithmeticity of 18 of the 40 hypergeometric groups corresponding to x minus 1 to the power 6. Here is a limitation of the SageMath program. So for the 22 remaining cases, we applied the SageMath program with the length k is equal to 15. This k determines the length of that particular word. The program returned a failure of finding any gamma satisfying the hypothesis of the proposition. So this shows in particular that if one of the corresponding groups is arithmetic and some gamma exists, then such a gamma has to be written as a product of at least 16 matrices in AB, A inverse, B inverse. Okay? So we just tested for k is equal to 15. K can be 1 million also. No? Means in some cases, suppose we get k is equal to 1 million. It's like the gamma is a word of length 1 million. That satisfies the condition of the proposition. Right? Then we get that is arithmetic. So not getting such gamma by using this program.
Failure means it did not give any output.
It did not give any output. It says that there is no such gamma. Actually, there is no such gamma of length up to 15. So if there is any gamma that satisfies the condition of the last proposition, that has to be of length at least 16. And like if you increase the length, no, the run time also increases. For case
How much run time for this was?
Maybe for case 50, it was taking 3 to 4 hours, and also depends on the CPU of your computer. Okay. So I mean, it doesn't actually not getting such a gamma of some particular doesn't mean that the corresponding group is thin. But it only means that if it is arithmetic and such gamma exists, then the gamma has to be of length
16 at least.
Yeah, correct. At least 16 also. We stopped at k is equal to 15 because of runtime of the computation. It may be noted that none of these 40 hypergeometric groups satisfy the criterion of Singh and Venkataramana. So, for example, if you consider fx minus 1 to the power 6 g this polynomial, then the corresponding hypergeometric group is arithmetic in SP6, and our program actually gives that gamma is this word. A square B square times A inverse B power 4 A B inverse A square, and one can note that the leading coefficient of F minus G is 6. But the SageMath program gives this gamma, and using that proposition, the arithmeticity of the corresponding group follows. 7 of the 40 hypergeometric. I will just take 5 more minutes. So
Sure. It's 8. 5 minutes is fine. No problem.
Okay. Yeah, thanks a lot. Thank you. So now means we also get that 7 of the 40 hypergeometric groups are thin. Actually, 7 of the remaining 22 are thin. We are able to prove the thinness. So we get the following theorem that the hypergeometric group gamma alpha beta corresponding to the 7 pairs of the parameters alpha beta, where alpha is this 0, 0, 0 and beta is any one of these 7 6 tuples. Are actually isomorphic to Z star Z. So basically we get the gamma FG corresponding to alpha beta, where alpha is 0, 0, 0, beta is any one of the 7 tuples. The corresponding hypergeometric group is a free group. In fact, that is isomorphic to Z star Z. And as a consequence of this, actually we get that these groups are thin. Like I have written this theorem in form of the parameters, then you know, no? Like alpha is 0, 0 means like f is x minus 1 to the power 6, and this corresponding to the first parameter, g is x plus 1 to the power 6.
So these are just the representative of the root. Right?
Representative of the roots, primitive roots of that particular degree. Right. So here, for example, this is x plus 1 to the power 4 times x square plus x plus 1. Okay. So So for example, the hypergeometric group corresponding to these two pairs, where f is x minus 1 to the power 6, x plus 1 to the power 6 is thin. To get the above theorem, we also use the ping pong lemma. So here is a version of a ping pong lemma that we use in our case. So let G be a group generated by 2 subgroups G1 and G2, and let E be the identity element of the group G. Suppose at least one of these 2 subgroups has order greater than 2 and Gx on a set W. And suppose there are non-empty subsets X and Y of W such that X and Y are disjoint subsets. G2 minus identity sends X into Y, and G1 minus identity element sends Y into X. Then we get that G is actually free product of G1 and G2. This is so simple, no? Means like this lemma means that is actually very helpful in proving some free. So how we apply this ping pong lemma in our case? So we apply this ping pong lemma by considering the standard action of gamma alpha beta on the real vector space R6. In our case, W is R6. And following the method of Brough and Thomas, we first change the basis to transform the matrix of the symplectic form in its standard form. And suppose K is the change of the basis matrix, and write U as K inverse AK and T is K inverse A inverse BK. So it's like we are writing A with respect to the new basis, and we are writing this C, which is A inverse B with respect to the new basis. Those matrices are T and U, and R is T times U. Then it follows that the hypergeometric group gamma alpha beta with respect to the new basis is generated by the cyclic group G1 and G2. G1 is generated by T and G2 is generated by R. Because we know that they are generated by A and B, so it's not difficult to show that this gamma is generated by T and R. So for example, I can denote G1 as the cyclic subgroup generated by T and G2 that by R. So in our 7 cases, G1 and G2 both are infinite. Means infinite cyclic means they are isomorphic to Z plus. And we define the 2 sets X and Y as the following, like X is like this union of some cones, and Y is union of Rj times X, means for all J in Z minus 0, and C plus and C minus are some cones in R6. And with this setting, we are able to verify the ping pong condition in our 7 cases. So we just proved that corresponding the hypergeometric group with in those 7 cases are free subgroups of SP6Z, so therefore they cannot they cannot be of finite index. Okay, so I think we can stop. Means there are some results about orthogonal hypergeometric groups also. So maybe we can talk sometime later.
Yeah, you can provide the slides. We can post it.
Yeah, slides correct. Means I will provide. Some there are some results. Substance in for the orthogonal case I could not discuss. Yeah, I'll provide the slide. Sure. So let us just stop at this point.
Thank you, Sandip.
Sorry, we should ask the Supriya whether it.
No, it was an excellent talk. Actually, that was my question going to be that other than symplectic, what are the cases you have been considering? So I think I will have to go through your last slides.
Yeah, that is there. Or maybe means when I visit IISER Pune, I will start from there.
Sure, sure.
Yeah, and it is written the way like it totally means it can be just some.
By the way, these 14 things that SP6, they also correspond to some monodromy of some varieties.
No, that is there, no? Means the Calabi-Yau variety is not the this.
So they are also
Calabi-Yau
the
threefolds.
monodromy of the Calabi-Yau varieties.
Means there are 14 families of Calabi-Yau threefolds. Actually, they fiber over P1 minus 3 points. So naturally, the fundamental groups act on some cohomological space of.
Yeah, and not 14. I'm talking this later 40 in the.
Oh, in this 40, yeah, this is a good question, but I don't know. Means I don't know. I have no idea if they also have any geometric significance like those 14 cases.
So is
No, I don't have any idea.
Result that the such monodromy of the varieties, like representation of fundamental group, can be realized as hypergeometric groups.
That will be great to see, but as far as I know, means I have no idea.
Okay. Okay, then that was my question.
Okay, I think those were all the questions. I think Devendra already asked interesting questions. So, okay.
Yeah,
so
thanks.
if there are no more questions, let's thank Sandip again. Thank you, Sandip.
Yeah, thanks a lot. Thank you. Yeah, it was very nice speaking here.
Yeah, thanks to Priya also for sharing this stuff. And see you sometime in person.
Sure,
yeah,
sure.
Sure. Yeah, we'll meet whenever I come to Pune. I'll meet both of you definitely.
See you.
Okay,
Sure.
see you.
Okay, Pawan, are you there?
Okay.
You can stop the things.
Okay, good night.
Good night.
Okay, good night. Yeah, thanks, Supriya.
Bye.
It was nice.
Thank you.
Bye.
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 अब रुकेंगे क्या सर जी 10 मिनट?
Okay. Yeah. वैसे YouTube चला गया ना?
Pawan, you can हाँ चला गया वो. नहीं अभी चल रहा है शायद. Pawan, can you stop the live streaming?
It's getting recorded. Recording also, no?
हाँ, both things. Pawan? Pawan, are you there?
Maybe his mic is not working. You cannot do anything then?
Pawan,
So you can join again, I guess.